gas that you have that much to burn, you ought to be recovering it anyways.
Yeah,
Well, I guess we'll begin here. So this presentation is all for you now here. So
And you are talking about the steam flow measurements associated with flares, I presume?
steam in general, but we'll talk a little bit about flare.
And off of boilers as well?
Yes. Yeah, I mean, it's mostly off of steam measurement everywhere, pretty much, and kind of the challenges associated with it. So we'll keep this shorter, a little bit, and kind of keep it and go from there. So, so my name's Tom Michalowski. I'm the product manager. This is being recorded as well, so I'm gonna give the full background here. With Panoramics for 20 years now, the global product manager, been an application engineer. Background is chemical engineering with an MBA. So this presentation's kind of just goes over some of the very, very steam basics, some of the challenges associated with flow measurement with steam, just how Ultrasonic really solves a lot of those problems, and some applications, again, everywhere, the applications. And we'll cover just some of the Ultrasonic basics as well. So that'll be kind of just a quick summary of it, and kind of I'd say my two takeaways I have kind of when we talk about steam measurement overall. Okay. We talked about steam, obviously it's all about water, right? Just, changing it. And I always show the phase diagram because my daughters are in high school now, and I always talk about the triple point: critical temperature, critical pressure. So we always, it's a good discussion. So obviously we're talking about, transitioning it from water to vapor is kind of the biggest thing. And you talk about boilers. Obviously boilers are the most common way, steam generators, you can even possibly heat exchangers, just if you want to use energy that's already existing in a refinery. But from that perspective, even anything, we talk about steam, curving it, from liquid to gas, need energy, and energy is money, right? So you want to conserve money, you want to conserve, as much as you can, because really at the end of the day, hits your wallet, hits your pocketbook, and going from there. So again, very basics. You have three levels of steam. You have dry steam, probably the easiest one to measure, just because they treat it like any hot gas at that point. It's above the kind of the saturation lines. The temperature, if you know the temperature, the pressure, the density. A lot of the mass flow calculations are done. Very simple. In this regime, quality is one. Again, we're talking about steam quality, talking about mass of gas to the total mass overall. Simplest application to really handle is because it's really treated as any hot gas overall. Most is saturated steam. Most of that's where people, drive. If you know the temperature. Process temperature, the saturation temperature, obviously saturation pressure. So from a measurement perspective, a lot of times you do mass flow from like a type of velocity or volumetric measurement, the temperature, you don't need both variables. So it's a little bit easier to do. Again, assuming 100% gas at this point, because assuming that, quality is one and kind of probably the most common and really no free water associated with it. But when we talk about steam, you also have to talk about wet steam as well. In an ideal world, I wish everything was, completely dry, but, just insulation, there's always reasons why steam will be wet. So at this, it's kind of under the dome. We look at specific volume to a temperature, the quality, really it kind of goes anywhere from 1 to, 0. Typically, again, 0.9 or better is what you want to see, from the steam measurement overall. But when you talk about it, naturally you got to talk about wet steam as well, because that's the real life. And we'll talk about a little bit more, because that's obviously one of the challenges you cover when we talk about steam measurement. So overall, why is steam flow measurement so hard? So I'm going to go over a couple of things. Obviously, it's high temperature. Obviously, it's over 212 degrees Fahrenheit. But the higher temperature you go, the more difficult it is. You have to really, whatever technology you're using, you have to talk about the sensing element you're using overall. So that has to be considered. And also sampling also needs to be based on the technology you're using. Sampling has to be considered. If you don't sample properly, you run into problems. So high temperature really can be an issue. Beyond temperature, high pressure as well. Again, depends on where you're using, might be 5-pound steam, but also like for power generation might be, 400-pound steam, 500-pound steam. So you deal with higher pressures overall. So obviously the sensing element needs to be able to handle up to a 1,500-pound, 2,500-pound flange class. But also you need to also think about, when you start dealing with those high pressures, about safety as well. You have to, you have the calibration involved, maintenance associated with it, high pressure. It's dangerous. So from that perspective, you need to take that into consideration as well. Then go the other extreme, low pressure. When having like 5-pound steam, it's a common application. Well, using like a differential pressure device, you only have a certain amount of pressure you can handle. You need to be able to also get flow through it. You need that delta in to get flow. So with lower pressure, you also think about what obstruction you're going to be using, what could be in the line overall. So low pressure is something you got to also be considerate of, and going from there. And then pressure drop. Again, steam's used all over, like for, let's say, district energy. You have long lines, steam, big lines. Need to consider what technology you're going to be using would cause a pressure drop or a differential pressure, and talk about pressure recovery as well. So from that perspective, that's again another consideration that needs to be thought of how you're going to handle it, especially a pressure drop. Is it something that you can handle or you cannot handle, and going from there. At the end of the day, it is energy, so you want to make sure you're using it as best as possible. Now, in the deal world, again, we talk about steam. You'd hope it's 100% gas. Reality is that's not always the case. Either poor insulation or insulation just over the years that's degraded. Talk some of these, this time of the year, some of the universities, say in the Northeast, might have had great insulation, but obviously it's worn down, and going from there. So be able to handle and tolerate wet steam is something that needs to be considered. Certain elements handle it better than others. So we'll talk about that in a little bit more detail. Another one is just steam. Again, ideally it was all 100% gas, but that's not always the case. Always have that dirty steam. Like 2 examples I know of recently that we've actually helped resolve is one was a geothermal type application, where again, it was steam coming out of the ground, which again, it was steam, but also some minerals associated with it started plugging other technologies. So something that would be more robust is something that needs to be thought about, and how you're going to even determine ahead of time. So you're not worrying about it, oh, it stopped measuring. So how can you kind of do some predictive monitoring or even diagnostics is a thought that needs to be in your back of your head overall. Another example, again, there was a steam measurement, but actually had some erosive and corrosive materials in it. And actually you started wearing down different technologies, kind of edges, and really started causing problems. So it caused it, really at that case, they actually came to us because they were continuing how to do maintenance associated with it. So again, it's another thought process of when you talk about steam. I wish it was all 100% gas. That's not always the case. Flow range. We talk about steam measurement, obviously you always have, hey, my ideal application runs in the nominal range. Well, you have also upset conditions. You also have lower usage conditions, just based on how you're using it, whether it's refineries, district energy, even in power. The amount of usage you're going to be used is going to be variable. So it's a discussion you need to always have when talking about steam flow measurement overall. And really, I think when we talk about flares, obviously high demand systems, more steam. So again, that rangeability needs to be there for that type of measurement, whether it's using 2 or 3 different elements, or you want to use one element to cover it all, and going from there. And then the last one, we talk rangeability, but obviously low flow range has become more important. Starting to see it over the last couple of years where people were like, hey, I'm running this much, that's good enough. Well, at the end of the day, that's money. And really to optimize and reduce those costs, you really want to know how much you're using. So knowing that low flow measurements become more and more important overall. And with that in mind, just some of those kind of difficulties, reliability and maintenance associated with it. You want to make sure it's up and running, and take that in consideration. Then the accuracy over the whole range as well. We talked about building rangeability, but to have the accuracy that you're going to be looking for in these changing conditions overall. So these are all the kind of considerations that need to come into place overall when we start looking at a steam flow measurement. So for ultrasonics, we'll kind of cover how it resolves a lot of these issues. First, the ultrasonic can handle high temperatures, can go up 100 to 450 degrees Celsius in steam measurements. So it has that rangeability. And we have 2 different types of technology we use, both ultrasonics, and we'll cover a little bit later, but we can handle that temperature overall. Pressure, handle anywhere from 150-pound flange class to 2,500-pound flange classes. So we can handle that rangeability. And we'll talk about the 2 ways we do it, but we do have the ability to handle that high pressure overall. And you'll see one of the examples that we actually isolate the transducer from those high pressure. So it's really no safety or issues you have to worry about overall with maintenance of the transducer. Low pressure. With our systems, we can again measure 5-pound steam because we have very little maintenance, very little restriction in the pipe. So it's really just the piping itself. Again, in most situations, we actually don't insert the transducers into the line. So it's really just that piping that's causing any type of pressure drop associated with it. And then we talk pressure drop, again, minimal to no pressure drop based on installation. Do we always put them at the ID or recess them? No. Sometimes for large pipes, you'll see some pictures. We actually, for installation, easy installation, we'll change the configurations and do that accordingly. So it really depends on the application, but again, it's very minimal pressure drop associated with it overall. steam. Again, we're tolerant wet stream. We actually can show some diagnostics. We'll see some of the gain and how steady the gain measurement is. So we can handle some of that, you know, the wetness of it. Like I said, we're measuring a two-phase system. No, we want to keep it as close to the gas phase as possible. Well, early on, we can start doing you'll see some of the diagnostics that we actually can tell, okay, something's going on there. It's not just the gas. We're seeing some difference. And that's what's important in that ultrasonic to provide some of these diagnostics that are so important. Then dirty steam. Again, I use the example of the geothermal application. You know, it's up and running. It's been fantastic overall, and we can kind of, you know, the way we design the transducers and how we insert them definitely helps out for sure. But we also use the diagnostics to kind of do some preventive maintenance. If it's really crazy, a lot of coding, we actually can tell you, you know, hey, it's going down. You probably need to do maintenance maybe 2 months from now or 3 months from now. But you can start looking, trending some data associated with which Ultrasonics does provide some of that details. And flow range, again, we can measure pretty much, you know, 0.1 to 150 feet per second. Kind of put it in a mass measurement. I can take a 4-inch, 100-pound system, talking about anywhere from 15 to 22,000 pounds per hour. So it's a very wide range overall. So from that perspective, it's again a great technology to use. Low flow measurement, it can measure it. I guess it's part of the big piece. You start some other technologies at a certain point, it just assumes zero. Well, we can measure it because T up equals T down. At the end of the day, it's just a raw measurement of transit time. So we know, okay, that they're the same, you know, guess what, really do stop the flow overall. And the last one is the kind of periodic maintenance associated with it. I think it's one of the values that we talk about total cost of ownership. It's not just the installation cost, but that maintenance associated with it overall. I mean, it's really the advanced stopwatch. It's really, you know, how ultrasonic works. There's no, you know, maintenance with it, and with the diagnostics, it really provides value overall with the long term. And then finally, the industry that's using. I mean, everywhere you talk about steam, you know, and steam flow measurement, you're talking oil and gas, power, renewables, utilities, you know, petrochemical manufacturing, just to name a few. Now go over some examples just to kind of walk us through here. Make sure I'm in time here. Okay. And is ultrasonics new to steam? No. I think this was still surprising that, you know, I get a lot of questions about, hey, can you do steam measurement ultrasonics? Yeah, we've done it for 20 years. It's not an issue of measuring, you know, at all, measuring steam with ultrasonic flow measurement. I don't think it's one of the natural thoughts people have when you look at for steam measurements. But again, this kind of was one of the papers that was presented back in 1999, I believe, and released our first dedicated steam meters in 2001. So we've been measuring steam for a long time, and I'll go through some examples, you know, showing how we're using steam today, using ultrasonic flow meters today to measure steam. And just some of the applications. Now we're talking about steam, you know, obviously in the kind of the process world, oil and gas, you know, obviously using heat exchangers, using them, you know, to keep, you know, fluids at certain temperatures that are desired. Using for cracking, you know, steam cracking, breaking down large molecules into smaller ones, so it's used there. Manufacturing, we'll go through one examples of how, you know, it's used for tooling, it's used for utilities, it's actually for power generation as well. And one facility actually, again, wanted to measure better to control some of that cost overall. Buildings, you know, obviously as we go to a, you know, district energy type measurements, as more people are going down that path, a lot of the steam measurements are larger pipes, larger runs, but they're trying to even get down to the, you know, the building level and even the floor level of kind of how they're using a steam measurement. Because at the end of the day, typically, like especially in that industry, they have one person, that's their job, is to save money, save energy, become green, go down the LEED certification route. So from that perspective, it becomes more important. And then for power, I mean, steam is still probably the most common working fluid that's used for you know, driving turbines overall, whether it's, you know, fossil fuels, nuclear, or even thermal, even geothermal, and even steam's coming out of the ground. Sometimes they'll switch it off with a different working fluid with a lower boiling point just to drive the turbine. But again, it's a capability of using steam to maximize its potential overall. And just some examples, you know, like one refinery here, multiple process units, you know, high pressure steam. You're talking about 16-inch lines, carbon steel, high temperatures, again, 700 degrees Fahrenheit, 600 pounds of pressure. See the rangeability in pounds per hour, 200, you know, 0 to 220,000 pounds per hour. We actually used a steam kind of transmitter style version with our BWT technology and FTPA buffers. And I'll kind of cover those a little bit at the end. So what those are, and the two different technologies. But just give one example here. Another example here is a medium pressure steam, again, 10-inch line, talking about, about 200 pounds of pressure. Again, the rangeability of going to 0 to 350,000 pounds per hour. Again, transmitter style, BWT technology, FTPAs. But you'll kind of see how they're kind of installed here on the picture here. You kind of see the nozzles are installed, as part of the piping here. And we'll talk about, we sometimes provide the flow cell itself, or we can actually, if it's something that already exists, we'll actually cold tap into the line to allow the alignments for something that's already in the field. So it gives that flexibility overall of how you want to drive your system. Another example, again, refiner number 2 here. Again, high, medium, and low pressure steam. Again, 10 inches to 24 inches. These are relatively big sizes overall. Temperature range, and this was 338 to 700 degrees Fahrenheit. You see the pressure, range from 100 to almost 600 pounds of pressure. Again, this one, using our different type of transducers, our T5 transducers with barrel holders. Not gonna, I'll show you some of those pictures, what they look like a little bit later in the presentation, but has a capability of doing low, medium, and high pressure overall. And it's just another example, again, that's our transmitter kind of right there, but you kind of see the transducer design. Again, mostly we always see ultrasonic being the tilted diameter, or kind of shooting across the pipe. Sometimes we'll actually install just on the top, just for either access or or ease of installation. So we have that flexibility of how we install the transducers. But again, the size of 16 to 24 inch lines, big steam lines with the rangeability is really a good advantage ultrasonic brings to the market. And then last one here for refinery heat exchanger. Again, 14 to 44 inch pipes, 50 to 600 pounds pressure. Handling the T5 for the medium low, temperatures and pressures, BWT for the high pressure systems overall. So again, why this one case, this one refinery came in there, why they choose ultrasonics at the end of the day. After we installed them, I think when it was one of our service engineers went in, he's like, oh yeah, we went because of the no pressure drop in rangeability. It was huge for us. That was kind of the comments they came back to us for, kind of the understanding of why, and going from there. Now we'll talk about steam, as part of the flare systems. Obviously, Lay and Tom will talk about, flares in more details, but obviously steam's part of it. And really, I'm not going to go into details too much, to be honest with you, about how steam assists and that piece of it. But I mean, one of the trigger points is when you measure the steam set rangeability. I mean, it comes down to that, hey, how do you handle that range, the off-peak time, the normal time, even load time, just that range overall. And how do you, again, you can't control unless you measure properly. And that's what steam provides, that, and the ultrasonic meter provides that kind of rangeability, accuracy over that full range overall. So with that, it's continued to take off. Obviously, steam's part of the, just one of the measurements beyond just fuel gas and the flare overall. And you kind of see that the picture here, we can kind of go over more details later on as well, but it's a big piece of it overall. And then kind of moving from petrochemical. Again, this is a situation where, this one customer wanted to save money. They really wanted to increase their, measurement range with higher turn down, but at the end of the day, it was really, the driving factor was the no maintenance. They were sick of the maintenance associated with it, having to keep calibrating, keep trimming, go into the field, change it. They see something more reliable, they can just go and just move forward. So with that in mind, they actually took a look at ultrasonics. They had one installed at a sister plant. So they actually compared it against another, I think this was a differential pressure measurement. And you can see the trending overall was almost just dead on. Absolutely performed. They were so happy. And with it, you kind of see even the design that we use against our BWT technology. It was a 2-pass system because accuracy and reliability is so important to them. They wanted to have redundancy overall. So it gave them that, capability of, hey, I don't want to touch anymore. I just want, even if I can compare 1 versus 2, there's a lot of, again, diagnostics and measurement you can do beyond just the flow measurement. And with that in mind, in this situation, again, you kind of see the temperatures and pressures, 15 to about 190 pounds of pressure. But actually this one, because we kept going, cycling through, it was actually just the cooling down, condensing on the bottom, and it wasn't really as much steady state. And that caused a lot of problems with existing technology as well, where ultrasonics can go from really from that rangeability from shut down to start up and going from there. Manufacturing. Obviously, in this one situation where a customer is using steam for from the boiler system for the process, for heating, and their power. All right, and from then it was like, hey, they had someone's like, we're just spending so much money on the boiler overall. How do we minimize that cost overall? It's being used for the process for metal rolling, for molding, coating, assembling, heating, and also power was all being used overall. So they want to reduce it. And obviously it provided from their perspective, ultrasonic provide that rangeability, no pressure drop associated with it, bidirectional in certain situations. And that really the signal strength diagnostics overall, beyond just the flow measurement, was really key for them. And you kind of see the rangeability. So it was all actually mostly low pressure steam, 20 to 40 pounds of pressure. But overall, it got provide that rangeability that they were looking for. And then with district energy, just one example is, this one government facility obviously was tasked to, hey, we're using for heating and cooling, we need to reduce our costs. Like, why are we spending so much money on heating and cooling? Let's reduce it. And traditional technologies were used, and really it was the maintenance associated with an uptime. And it's kind of, hey, what do we do to improve, keep it up and running, and not worry about, the trend, make sure you get the trending data associated with it to make the right decisions to how to reduce overall. And that was actually a big piece of it, because they find out the maintenance associated with it, and we're getting the trending information they needed. So it kind of was cyclical. So they really wanted to break the cycle. So they actually looked at ultrasonics for the steam, and we usually would start clamp on liquid systems for the kind of the chillers as well to provide those measurements. So it was good usage of ultrasonics as a solution. Really, the no maintenance over the long term was the big key. And then I would say really on the high pressure side, for sure, a couple of power plants that we've used, these systems associated with it, and kind of give you an idea of, these are high pressure systems, high temperature, high pressure. These are all 1,500 pound. Actually, one was 2,500 pound flange class here. So these are big lines. You can kind of see almost, this was actually 535 degrees C. We actually had to use a special gasket associated with it, because typically we don't do, we typically say 450 degrees C and kind of go from there. As a situation, we actually went higher. With that in mind, we take a look at it. It was a kind of design we went through. We were the handle up to about 1,300 pounds of pressure. So again, a great application. It actually did a similar application in a second power plant as well. You can kind of see the temperature and the pressure associated with that we were able to measure. But again, those are kind of some of the customizations that we look at ultrasonics that can be done, but we handle on a kind of case-by-case basis and going from there. And I've kind of covered it through the presentation here, but kind of just gives a quick summary of the, reliability, bidirectional, low end, wide rangeability, no obstruction in the flow, tolerant of wet steam, high temperature, suitable high temperature, no maintenance. Again, accuracy is typically about 0.5 to 1% that you can expect in an ultrasonic meter. So it provides that kind of capabilities overall. And then quickly, just go over just kind of, we talked about ultrasonics, like some people just, if you understand the basics, obviously we talked about ultrasounds, it's anything over 20 kilohertz of a sound wave, again, used from imaging to NDT to chemical cleaning to flow measurement. It's always using ultrasound. And obviously transit time technique is probably the most common, not the only one, but the most common one used in the industry to measure flow. So again, it's very simple. It's kind of two transducers kind of typically at about a 45-degree angle. You send a signal back and forth. And when the signal is going with the flow, speeds up, goes against the flow, slows down. And that timing difference is proportional to like a velocity measurement. And that's all the transducer sending signals back and forth. So it's always, the analogy is kind of rowing on a boat. Going, with the flow is pretty easy. Against the flow, get your arms really tired. So that's pretty simple overall. And just a quick kind of video just showing, how it's working. It goes against the flow, slows down, goes with the flow, speeds up. So again, the time difference is really proportional to that velocity overall. And then just a basic system. I kind of covered, we've talked about the transducers, electronics, but really an ultrasonic flow meter has electronics, kind of the brains of the system that takes the signals in and kind of does all the timing algorithms, is all in electronics. You got the transducers that actually, create the ultrasound overall. Then you got to somehow have to put it into a holder or kind of put it into your system. That's what we call the transducer holder. Then you have either a flow cell or a nozzle. That's the piece kind of right here. The flow cell is the whole piece, or if the piping already exists, we'll just provide that kind of nozzle. It's kind of associated right there based on the system. And then if you need some type of mass flow, we need to take in the temperature and pressure. Because again, ultrasonics usually, again, it's the velocity measurement, the IDs of the pipe, you get to volumetric. If you want mass flow, you need that temperature and pressure. And it broke it down into kind of, the two classes that we use for measuring steam, kind of like low and medium temperature and then high temperature. The reason is we use ultrasound, but we use the design two different ways overall. Most common way you kind of see in this picture, electric crystal is really at the end of the transducer, probably the most common design that you'll use. And that kind of see, it's really in the nozzle, you'll kind of see it shoots from that really edge and sends the signal. For high temperature systems, the transducer is actually located here and goes through what's called a bundled wave. And we do a bundled wave. And I'll show you the picture of kind of what it looks like and so you have an idea, but it's done that way just because you can't operate the transducer will die if you operate at those high temperatures overall. And I'll show you examples in the pictures of that as well. But just kind of from a system, the typical one, I think for the lower pressure, obviously you have the electronics, again, 1 or 2 path, does the communication and sends it to the control system based on 4 to 20, Modbus, HART, whatever needs to be based on your system. You have the transducer, probably the most common one here with, again, this normal temperature with the crystal on the side, to be titanium construction because it's really just durable overall. Again, handles really designed based on the pressures and temperatures. We have a holder here. I think this is our flange holder. Again, just allows us to mount it onto a nozzle just with a flange connection. And then we'll show kind of the flow cell and the nozzle. Again, that's how we get it into the final assembly here. So when we talk about flow cell and nozzles here, obviously the flow cell is like the piece of piping that's kind of shown here. It could be simple as, I think this was like a 12-inch, 900-pound system. This was like I think this was a 2,500-pound system. And kind of see the designs can vary. We've been in some of the history of panometrics. We've done PVC, we've done multiple materials, so it can change based on the design, the pass needed. Again, more pass, typically the more accurate, more resolution you have. But again, for steam, again, most of the time it's like 1 or 2 pass system going from there. But I also talked about, hey, sometimes you have lines that you don't want to stop. You just want to be able to do a cold tap in the system. So we'll just again provide these nozzles that's kind of shown here. And we use the existing pipe associated with it. So it gets a cold tap into the system overall. Now the bundle wave, this is for the high temperature, because again, you get to a certain point that the piezoelectric crystal will go past its Curie point where it'll just kill the crystal overall. So from that perspective, you got to find a way to, separate it from the temperature. So, so what we do is we actually put it on at the end of this, what we call a bundled wave. And it's almost think of it as like a bunch of little tubes inside of one big tube. Short analogy, and it sends a cleaner signal through versus just like a solid piece of pipe. And we do this because obviously it's a cleaner signal, but also keeps it to that, we can actually work an application about 450 degrees C or higher, as you've seen. But again, this is the transducer right there associated with it. So it's isolated from the process here. And you kind of see like an example here, we got some of the liquid ones go to 600 degrees C. This is the process, but the transducer is kept cool here from that bundle, using that bundled wave. And kind of taking this kind of just a quick simple animation here. But see the transducer again. There's the transducer. It's located outside, and it shoots that rod, and then kind of isolating here. Why? Because that temperature is so extremely so hot. Again, it keeps it at the cooler condition and allowing that ambient temperatures to cool it down. So it gives that flexibility. And we also do some other calculations along that as well to kind of for timing and going from there. But that's the reason why we use that bundled wave technology is so advantageous. And just some installation examples of bundled wave. You kind of see how it's kind of installed on the outside here. You kind of see you're at those higher temperatures. There's typically the pipes are insulated. Just kind of show some examples of insulation that's associated with it. Again, sometimes it's 2-path here for redundancy. But again, it's all using that very, very, very high temperature for these applications. Actually, pretty good timing here. So, my 2 kind of takeaways. First one, again, we talk about steam measurement. Make sure, again, work with who we're going to deal with for the steam measurements. Make sure you get all the information. I guess I always say the analogies. Apples are not the same as oranges. So we want to make sure when we go out and work with, for any type of steam measurement, we don't just ask for, hey, what's your flow rate? We ask for temperature, pressure. Okay, what's your pipe condition? What's your flange class? What's your expectations overall in the measurement? Just to get a better understanding. So again, it's better to resolve it now than when it's installed and it's not working properly. You know, that's the biggest piece. That, again, one of my takeaways is always, you know, either if you have a data sheet you're providing, if you don't, we'll provide one to give you, you know, and we'll talk you through exactly some of those questions to make sure, again, resolving, you know, what your expectations are in that measurement, because it's so critical to have the communication ahead of the time versus after the fact. That's kind of my one takeaway that with steam measurement is always that piece of it. Make sure we talk it through. And the second piece is, I would think, ultrasonics. It's not a common thought when people's like, hey, I want a steam meter. Ultrasonics is probably not the first one, but it should be, because really at the end of the day, we talk about long-term measurements. And actually had one university came back to us and just said, man, you know, I love your meters, because once I install them, I never touch them again. You know, I like, and it's one of the things that I resonated through is like, okay, you know, kind of explain a little why you like. It's like, hey, honestly, once it's installed, we work with you guys. It's overall, again, it's that long-term reliability at the end of the day that they can maintain for years to come. And they've had some meters, again, for like this one location has had over these 10 years that I know of. And I've had some, I know, installed some of the refineries shown here for like 20 plus years. But again, it's that discussion ahead of time, working with specifications, and then ultrasonics really as a technology with diagnostics is really valuable overall. So I think that's the last slide.